Alright guys, happy Thursday. You should have in front of you a rather large packet, about 33 questions long. Your goal is to watch this video, and as I go through it with you, try to complete this packet. I am going to count it as a quiz grade, and it is due by the end of the period. Okay, so I want to discuss the 7 rules for exponents that we learned in section 5.1. The first one was any number, so we're just going to refer to this as any number. If we raise it to the 0 power, every time we get 1. Could be 50 to the 0 power, it could be 2x squared to the 0 power. Anytime you raise a quantity to the 0 power, you get 1. The next rule we'll look at is that when you have the same base, if I say a to the second times a to the third, that is the same thing as saying a to the fifth. We add these up. A way of proving that to yourself is, let's pick the number 2 and use that as our base. Well, based on what we said above, this should be equal to 2 to the fourth, because we added them up. And what is 2 to the third? 8, and 2 to the first is 2, and 8 times 2 is 16, and 2 to the fourth is 16, so that should make sense. The third rule we looked at, if you have a fraction, so we'll just say a over b, and you raise that fraction to the, let's just say x power, just making a blueprint, that is the same thing as saying a to the x over b to the x. We raise the top and bottom of the fraction to whatever power we're working with. Whenever we are simplifying fractions, if we're dividing, let's say I have x to the fifth up top and x to the third on the bottom, that leaves me with x squared on the top. Remember, we think of these as objects, so if I have 5 objects up top and 3 on the bottom, when you start canceling, if you have 1, 2, 3, 4, 5, and 1, 2, 3, and you start to cancel these, well, that one goes with that one, and that one, and I'm left with 2 x's up top, which is the same thing as saying x squared. When we mix in negative exponents with this, first off, a negative exponent tells us to do what? It tells us to flip it. So if I said I have a excuse me, to the negative second power, tells us to do 1 over a squared. If I have this with a number, say I have 2 to the negative third power, that tells us to make this 1 over 2 to the third, and 1 over 2 to the third is 8. When we do this in combination with the division we just looked at, so let's say we have a squared over a to the negative third, b to the negative fourth, and b. Well, the negative exponent tells me to flip it. So I see a to the negative third down here. It tells me to bring it up. Okay, and that gives me a total now of a to the 5. So there's 5 of these now. I had 2 and I brought 3 of them up. In this one here, I have b to the negative 4, and it tells me to flip it down. I already have 1b right here, and when I bring 4 more of them down, that's going to give me b to the 5th on the bottom. The next rule we looked at was when we take something that is a power to a power. And the rule is when you raise a power to a power, you multiply. A numeric example would be 2 to the third and all of that to the fourth. That should give us 2 to the 12th. Okay, when we have something in a quantity, example, let's say we have 3x squared y, and we want to square that. So we have a few different things going on here. I want to apply this second power to everything I see. So this becomes 3 squared. X to the power to a power we multiply, giving me 4, and y squared. 3 squared is 9, and then leaves me x to the 4th y squared. Okay, so let's look at some more examples here. If I take a quantity, and this might look similar to number 1 on your packet, and I say, let's say I have the quantity of 4x squared, and let's raise all of that to the negative third power. Well, I know that when I have this quantity here and I want to raise it to a power, I'm going to apply this negative 3 to everything. So this becomes 4 to the negative third, and power to a power I multiply. Now this is x to the negative sixth. This is the same thing as saying all of this over 1, if it helps you with the fraction mentality, so you have something on the top and something on the bottom. The negative tells me to flip it. So this is now really 1 over 4 to the third x to the sixth. And then I ask myself, well, what is 4 to the third? 4 times 4 is 16, and 16 times 4 is 64, leaving you 1 over 64x to the sixth. If we look at the second one in your packet, something similar that we could compare to, let's say we have 2 over 3x, and we're going to take this and raise it to the fourth power. When I take a fraction and I raise it to a power, I raise the top and I also raise the bottom. So this becomes 2 to the fourth over 3 to the fourth x to the fourth. Notice on the bottom we apply this fourth power to the 3 and the x. This gives me 16. 3 to the fourth is 81 x to the fourth. Okay, let's take a look at one with division. So let's say we have, put a bunch of letters out here. A, B, C, D, A, B, C, D. And let's give them a bunch of exponents. Okay, and we want to simplify this. So, first thing I do is I look at my A's. I see that this is a negative 4 up top, which tells me I need to bring that down to the bottom. So if I bring 4 down to the bottom, I already have 2 of them. Gives me a to the sixth. I look at my b's here. They're both negative, which means I'm going to flip-flop both of them, meaning I'm going to bring 4 up and 2 down. So now I have b to the fourth over b squared. We'll cancel that in a second. The next one, the c's. I have 2 up top. I have negative 5 on the bottom. Negative 5 tells me to flip it up. I already have 2. I bring 5 more up. Gives me c to the seventh. I look at my d's. There's 1 up top, negative 4 on the bottom. That negative tells me to flip it. If I have 1 up top and I bring 4 more, it gives me a total of d to the fifth. And then the only thing we have left to do is simplify these b's. So our final answer is, on the bottom, a to the sixth. And then up top, I had 4 b's. 2 on the bottom, 4 up top, 2 on the bottom, leaves me 2 up top. And then nothing else needs done with your C and your D other than just to rewrite it, and this would be your final answer. Okay, the next part of Unit 5, Section 1 that we learned was about the radicals. And we know that when you have a radical, the number up here is your index number. And this is the part that determines everything you do in your problem. What is the index number? And we know that if there is not an index number written, we assume it to be a 2. So if our index number is a 2, we're going to be thinking about perfect square roots if it's a 2. If it's a 3, we're going to be looking at perfect cube roots. 4 is fourth roots, and 5 is your fifth roots. So before we start doing these problems, I want you to make a list until you're really familiar with these numbers. Make a list. And these are the numbers we're going to be trying to use. So for perfect squares, what are my perfect squares? 1 squared is 1, 2 squared is 4, 3 squared is 9, just continuing on, 16, 5 squared is 25, 6 squared is 36, 49, 64, 81, and 10 squared is 100. That is more than enough to get you through the problems in this packet. For the third roots, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64, and 5 times 5 times 5 is 125. For the fourth roots, 1 to the fourth is 1, 2 to the fourth, 16, 3 to the fourth, 81, 2 to the fourth, 256. For the fifth root, 1 to the fifth is 1, 2 to the fifth is 32, 3 to the fifth, 3 times 3 times 3 times 3 times 3 is 243. And again, 243, plenty big enough. So if you look at these, the first thing we're going to ask ourselves every time, what is my index number? And then go to the list that matches up the index number. If it's a square root, I'm going to be thinking about my perfect squares. If it's a cube root, we'll be right here, fourth root, and fifth root. So actually, the higher your index number, kind of the easier it gets because you have less choices to figure out what goes into it. Okay, so keeping your perfect root list nearby, let's take a look at a problem. Let's say we'll do 1 for each index number. So this is a squared root problem. So the square root of, I don't know, let's say 40x to the third y to the sixth. So squared root, so go to your squared root list that you just made. What is the biggest perfect square that goes into 40? And then the question I ask myself is, how many times does it go in? So if you remember, we kind of learned how to write these as, we said, perfect square times whatever, and then put your letters right at the end. So I say, what is my perfect square? The perfect square that goes into 40 is 4. How many times does 4 go into 40? That's my whatever you need number. How many times do I have to multiply this perfect square by to recreate 40? And 4 times 10 gives me what I'm looking for. And what letters did I have? X to the third, y to the sixth. So now remember, this index number is a 2. Even though it's not written in the problem, we still have to think of it as a 2 up there. So now I go through and I simplify. What is the square root of 4? It's 2. I make my root symbol. Can I take the square root of 10? No, so I leave it underneath. And when it comes time for the letters, we do division. I take the index number, I divide it into the exponent of my letter. 2 goes into 3, how many times? Once, and then I put the remainder underneath. 2 goes into 6 for the y's, how many times? 3 times. There is not a remainder, and there's my answer. Okay, let's do one with a cube root. So, say we have the cube root of 54 x to the 10th y to the 15th. Cube root. So go back to your perfect cubed roots. Here's our list right here. What perfect cube root goes into 54? 1, well, 1's not going to be important here. Is it 8? No. 27? Yes. 64? Well, that's already bigger than 54, so we can rule out 64 and 125. So 27 is the number, the perfect cube root that goes into 54. How many times does it go in? It goes in twice. And then I carry my letters along. Now we run the same process. What is the cube root of 27? In other words, what number times itself 3 times gives me 27? And 3 times 3 times 3 is 27. Therefore, the cube root of 27 is 3. My leftover number is the 2. And now I run the letters the same way I did in the squared root problem, only now I'm dividing a 3 into them. 3 goes into 10 how many times? Goes in 3 times with 1 left over. 3 goes into 15, 5 times evenly, nothing left over. Make sure you put your index number up top to show that this was a cube root problem, and you are all done. Okay, let's try a fourth root problem. So let's say we have the fourth root of, let's throw a number out front this time. Let's say we have a 3 out front. Now this 3, think of it as a multiplier. So this is 3 times the fourth root of whatever we're about to make up here. So when we pull numbers out, they're going to get multiplied by 3. So let's say we're going to say 3 times the fourth root of 32x to the 7th. So again, I want to pull back up my perfect root list right here. And I say, what's my index number? It's a 4. So I want to look at my fourth roots. Which fourth root goes evenly into 32? 1, again, we said we're not interested in. 16, that does go into 32. And as I said, as the roots get bigger, it kind of gets easier because clearly 81 and 256 don't go in. 1 goes into everything, so the only number that would even make sense here is the 16. How many times does my 16 go in? It goes in twice, so I'm going to write this as 3 times the fourth root of 16 times 2, x to the 7th. Okay. So now, 3 times, what is the fourth root of 16? And don't say 4, because it's not the squared root. It's the fourth root. So what is the fourth root of 16? In other words, what number times itself 4 times? 2 times 2 times 2 times 2 gives me my 16. So the fourth root of 16 is 2. So the number I'm actually pulling out here, I wrote small here, is a 2. Now, normally we just put that 2 out front. There's already a 3 out front though, so instead of this 3, I'm going to scratch this out now, it becomes a 6 because 3 times 2 is 6. What's left over? This number right here that was already underneath, so I have a 2 left over, and now I run my letters the same way. Index number is a 4, it goes into 7 once, remainder 3, put my fourth root symbol right there, and we are done. Same thing goes with fifth root. I don't really think we need an example. Same premise, use your fifth root list, so 132, 243, and so on. Okay, continuing our lesson, you should be on the second page, or the back rather, of the front, so the 13 to 20 side of your assignment by now. We're going to look at what it means to multiply two radicals. And when you multiply two radicals, it's very simple. You just multiply. In order to do that, though, you need them to have the same index number. So if I say the square root of 2 times the square root of 18, they have the same index number, that being a 2. I can multiply these, and that gives me the square root of 36, and the square root of 36 is 6. So multiplying, pretty simple. Just take the two numbers, shove them together, and multiply as long as this index number up here is the same. If it's not the same, you can't do anything, just let them go. Let's try one with letters. So let's say that we have the square root of 3x times the square root of 8x squared. When I multiply these together, this gives me 24x to the third, because remember, x to the first times x squared is x to the third. You'd add those up. When I go to break this down now, it's a square root. Go back to my perfect square list. What perfect square goes into 24, and the biggest one that goes into 24 would be 4. 2 times 2 is 4. If you think about the other ones, what do we have? 9, no. 16, no. 25, it's already too big. So we're going to rewrite this as 4 times 6 times x to the third. What is the square root of 4? 2. And what are we left with? 6x to the third. And we need to break the letter down. Your index number is in 2. 2 goes into 3 once. Remainder 6. Then you have 1x underneath. Okay, as far as division goes, same principles as multiplication. You need the same index number. If I told you we have the square root of 16 divided by the square root of 4, this is an easy one because these are both already perfect squares, so this is actually a way to kind of prove this is correct. But the rule says that if they have the same index number, and in this case they do, they were both squared roots, then we can make one big square root and just say that, 16 over 4. And what is 16 divided by 4? It is 4. And what is the square root of 4? 2. If we did this the other way around and actually did the math, so let's take this same problem and come down here. If I say the square root of 16 over the square root of 4, what is the square root of 16? 4. And what is the square root of 4? 2. And 4 divided by 2 is 2. So the part in blue here just kind of serves as a proof almost to show you that when they have the same index number, you can just combine them under the radical, because typically you're not always going to have ones that are perfect squares. Example, let's say we made the square root of 32 divided by the square root of 2. And these ones we can't take the perfect square just like we did up here, but I see that we're dividing. I see we have the same index number, so I can combine these under one root and then say this is 32 over 2, and 32 over 2 is 16, and the square root of 16 is 4. Okay, the next part of our lesson is on rationalizing the denominator. So we'll label this here, rationalize the denominator. So what is the denominator, first off? The denominator is the bottom part of your fraction. And rationalizing it means simply we do not want to leave a square root in the bottom of our answer. And we're going to look at the way, or the ways that we go about getting rid of this square root. So in a real basic example, let's say we have the square root of 3 over the square root of 5. It's okay to leave a square root in the top, but for right now we do not want a square root in the bottom of our answer. So to fix this, we're going to multiply the top and the bottom by that square root that's bothering us down there. And when I do that, what did we just learn about multiplying here a second ago? Multiplying roots, you just shove them together as long as they have the same index number. So up top, now I have the square root of 15, and on the bottom, well, what do I have? 5 times 5 is 25, so it's the square root of 25, and what is the square root of 25? It's 5. So a quick lesson here is that whenever you multiply two exact things together that are roots, like example, if I say radical A times radical A, I'm just left with A. If I say radical stuff times radical stuff, and this stuff is the same exact stuff, when you multiply them, you're just left with your stuff. So this should give you a shortcut when you're going through these. You should not really need that middle step that says radical 25, which then leads you to 5. Let's take a look at one in terms of cube roots and how they differ. So if we look at the same exact problem, radical 3 over radical 5, but instead of making them squared roots, let's say we have the cube root of each of these. How are we going to go about getting rid of this cube root of 5 in the bottom? Well, it's the same process, but when I go to multiply now by the cube root of 5, and the cube root of 5, what's going to happen here? Well, 5 times 5 is 25, but I can't take the cube root of 25. It doesn't do anything for me. It would just be the cube root of 25. I'm still left with a radical in the bottom. So we need to do it one more time. Why? Because it's a cube root, so you need 3 things. And there's the bell. Okay, continuing. So when I say 5 times 5 times 5, okay, that's 125. And now I can take the cube root of 125, and that gives me 5. Up top, I'm going to have the cube root of, well, what do we have? 3 times 5 is 15, and 15 times 5 is 75. So I'm left with the cube root of 75 over 5, and now I've been able to get rid of that radical in the bottom. Okay, the next part of our lesson, this is new now. Adding and subtracting fractions. Adding and subtracting, much more complicated. Not much more, but more complicated than multiplying, dividing. To add and subtract, you need 2 things. So to add, the marker's dying here. To add or subtract, you need 2 things. And the 2 things you need are same index number, and you also need the same number under the radical. You need 2 things to happen to add or subtract. You need the same index number and the same number under the radical. So an example of something that would work. The cube root of 4 plus 2 cube roots of 4. So this is really a 1 out front, and we want to think of these as objects. I have 1 of these, and I have 2 of these. And these are the same thing. So I've met my criteria. Same index number, same number underneath. And when I have this, I just add my objects. I have one of these and two of these, therefore now I have three of these. If at any point in time the index number didn't match, or this 4 number underneath was not the same number, couldn't do it. You'd be stuck. So let's take a look at one such as 4 square root of 2x plus 5 square root of 2x minus 3 square root 2x. Again, this is for adding or subtracting. What do I see here? 2x, 2x, and 2x. Index number matches across the board, so I can add my objects. 4 of them and 5 of them is 9 of them, and 9 of my objects minus 3 of my objects is 6 of my objects. Okay, let's look at one where we're adding and subtracting. So again, maybe another counterexample before we do that. Let's say I have this 2 square roots of 2x plus 3 square roots of 3x. There's nothing I can do here. Why? Because the number underneath doesn't match. Likewise, if I said 2 cube roots of 2x plus 3 square roots of 2x, nothing I can do. Why? My index number doesn't match. And my two criteria for this to work were same index number, same number underneath the radical. Another example though that might throw you off but does actually work, similar to number 23 on your packet. Let's say I have 3 radical 8 plus 2 radical 50. At first glance, looks like there's nothing I can do. Index number is the same, but the number underneath, it's not. However, you can fix this so that it will work. How can I fix this? Well, break down each problem or each part of this problem separately. So when I look at this, I say, well, square root of 8, index number is a 2. I'm thinking about perfect squares. What perfect square goes into 8? So 4, and then times 2. So this becomes 3, 4 times 2. And then over here, what do we know? This is really what perfect square goes into that? 25. So 25 times 2. And now we update. Well, what is the square root of 4? 2. So I pull this 2 out. There's already a 3 out here. My multiplier gives me 6 radical 2 plus this 25. When I pull it out, it becomes a 5. And 5 times 2 is 10 radical 2. And now, look what I got. Same number underneath, same index, good to go. 16 radical 2. If you had more than 2 things, such as number 23, there's 3 parts to it. Do the same process. See if you can get the same number underneath for all 3 of them. Okay, next up we're going to look at multiplying, kind of in terms of foiling a number in its radical. So if I say we have 2 plus 4 radical 3, and we're going to multiply that by 1 plus 2 radical 5. Okay, so we're going to run this like a FOIL problem. First times first is 2. Now, when I go to do my outer, let's do a little side lesson here in terms of multiplying. So if I say, just a side example, if I say 2 radical 5 times 3 radical 6, very simply, you multiply the number with the number, and 2 times 3 is 6, and you multiply the radical with the radical, and 5 times 6 is 30. So this is kind of our process for when we multiply, which is what we're going to need when we FOIL. So taking this idea, I'll give you 1 second here to look at it, and we're going to take this idea and come back here now to the FOIL. So first times first is 2. The outer, 2 times 2 is 4. This one doesn't have a radical, so just bring the 5 along for the ride. I come to my inner. Again, we've done first, outer. The inner now, number times number gives me 4. There is no radical to go with it, so just bring the 3 along. And now last times last. This part here is where we're going to look at what we did down here. So 4 times 2 is an 8, and radical 3 times radical 5 is radical 15. Now I look at these and say, is there anything I can combine? Well, what do I need to combine? In order to add and subtract, I need the same index number, and I need the same number underneath. And I do not see the same number underneath anywhere. Now, in some of these problems you will see the same numbers underneath, at which point you then can combine them by adding or subtracting. Okay, let's look at what it means to square a quantity. So if I said we had 2 plus radical 5 quantity squared, when you square a quantity, well, what does it mean? If I say 3 squared, you know the answer is 9. What are you really doing, though? You're taking the 3 and multiplying it by itself. So when I take this quantity and I square it, I'm taking this entire quantity, which is 2 plus radical 5, and I'm multiplying it by itself, 2 plus radical 5. And now we created a FOIL situation. First times first is 4 outer. 2 times radical 5, pretend there's a 1 out front there, even though we don't write it, but it's still there. 2 times 1 is 2, bring the radical 5. The inner, same process, plus 2 radical 5. And last times last is radical 5 times radical 5, which is radical 25, and radical 25 is 5. Now, there's a lot of combining to be done here. First, I see the numbers. Those are easy. 4 and 5, that gives me 9. And now I look at my inner. Same number underneath, same index number, tells me I can combine these objects. I have 2 of these things and another 2 of these things. Gives me a total of 4 of those things. So your final answer would be 9 plus 4 radical 5. Okay, taking a look at number 27, it says rationalize the denominator. And what did we learn about rationalizing the denominator a few slides ago? It means we want to get rid of the radical from the bottom. So if we look at a problem that says, let's try 2 plus radical 3 all over 1 plus radical 5. And if you remember back to Unit 4 when we talked about a conjugate, remember a conjugate was the thing you guys thought it was really hard at first, and then as we started talking about it, like a couple minutes, it was actually probably the easiest question on your test or your quiz. And we said, well, what was a conjugate? So we come down here, and a conjugate, side example, conjugate. If I said I had, remember the A plus radical B, and we said it was a 0 or an answer, its conjugate, also known as A minus radical B, would also be an answer. And we said the same thing applied to imaginaries, A plus BI, and then therefore A minus BI. So the rule for this, taking this right here and bringing it back up to here, whenever I have more than just a radical on the bottom, in other words, it's being added to something, okay? To get rid of it, we're going to multiply the top and bottom by its conjugate. So what is the conjugate of the bottom? Well, instead of 1 plus radical 5, we're going to multiply the top and the bottom by 1 minus radical 5. Now, you have a top and a bottom that both need FOILed. So you're going to FOIL the top and FOIL the bottom. So if I look at the top, FOILing the top, first times first is 2. The outer, a positive times a negative is a negative, negative 2 radical 5. The inner is a positive radical 3, and last times last is a positive times a negative is a negative radical 15. On the bottom, FOILing out, first times first, 1. Outer, minus radical 5, inner, plus radical 5. Last times last, minus radical 25, which is just a 5. Okay, going through here now and seeing what we can combine. On the bottom, negative radical 5 plus radical 5. Index numbers match, numbers underneath match. Those cancel out. What am I left with? 1 minus 5, and that's negative 4. Up top, I don't see anything that goes away. I have a number, radical 5, radical 3, radical 15. So you would just take all of this and move it on over. Okay guys, last part. So we're looking at 28 to 33. So before we try any of these problems, we need a little lesson here on what rational exponents are. Things that are rational, it means we're dealing with a fraction. So it's an exponent that's a fraction. So the easiest way to look at this is, let's just make a blueprint. X raised to the a over b. So here is my letter, and I'm going to raise it to some fraction. So we need to know what this fraction tells us to do. And here's what it tells us to do. X to the, instead of a, we're going to call it power. And instead of b, we're going to call it root. X to the power over root. So let's think about what these words mean. Power means to raise something up, raise it to a power. Root means to take the root of it, take the square root, the cube root, the fourth root, the whatever root you're working with. So if we were to do a very generic example, let's say we have 4 to the 3 over 2 power. And now I'm going to teach you a trick here. Always do the root first. So this tells me to take the square root of 4 and then raise that answer to the third power. And another way of remembering this is when you raise a power, you're raising it up. So the top part of the fraction, up. Top, power, power means to raise it up. So the top part of your fraction is always the part you raise to that power. So when I do this, the square root of 4 is 2, and 2 to the third is 8. Let's try some other ones here when we involve letters. Let's say we do 16x to the fourth, raising all this to the 1/2 power. So what does the 1/2 power really mean? It means I want to raise things to the first power, but not until I've taken the squared root. Well, when I raise things to the first power, does that change anything? If I say 1,000 to the first power, it's still 1,000, right? So nothing changed. So in other words, I'm just going to take the square root and then do nothing. So in other words, I'm just taking the square root. So raising it to the 1/2 power is another way of saying taking the square root. So side note here, if I say the 1/2 power, that's the square root. Well, what's going to be the cube root? The cube root would be the 1/3 power. 1/4 would be the fourth root power, and so on. It's very important that you recognize these. So if I just say 16 to the 1/2 power, that's the same thing as saying, well, here's my root. It says, what root am I going to do? The second root of my number raised to what power? The first power. Well, raising something to the first power doesn't change anything, so it's really just the square root of 16. If we add letters into this, so back to the one we just looked at, well, what did we learn about this situation? We can apply this 1/2 power to everything. So this is 16 to the 1/2, x to the power to a power we multiply, and 4 times 1/2 is 2. What am I left with now? It says 16 to the 1/2 power. In other words, the square root of 16. What is the square root of 16? 4. And what do I have left? X squared. Okay, let's try one more. Let's try one with a negative exponent, make it a little bit tricky. Let's say we have 16x to the 8th power, and we're going to raise all of this to the negative 1/2. We're going to raise all of it to the negative 1/2. What does all that mean? So, let's say we make this 16 to the negative 1/2, and then power to a power we multiply. So now that's negative 4. Well, what does a negative power tell me to do? It tells me to immediately flip it. So this is really 1 over 16 to the 1/2 x to the 4th. And what's the 1/2 power tell me to do? Power up top, root on the bottom. Do the root first. So this is really 1 over 4 x to the 4th. Okay. Okay, so this is the last problem we're going to do for the video. Let's say we have 27x to the 6th in parentheses, and we're going to raise this to the negative 2/3 power. Same principle. Take this exponent and distribute through. So this is 27 to the negative 2/3 and x to the negative 4. How did I get negative 4? Well, off to the side here. What do I know? Power to a power we multiply. Well, what is 2/3 of 6? Hopefully we say 4. If we don't, 6 over 1 times 2 over 3. Remember that's negative. Multiply fractions, tops and bottoms. 6 times negative 2 is negative 12. And negative 12 over 3 gives us what? A negative 4. So back to the problem. Put this over 1 to create that fraction effect. So the negatives tell me to flip them. This becomes 1 over 27 to the negative 2/3, x to the 4th. Well, what's different here about this one? My power now is no longer a 1. So this is not just a cube root, it's the cube root of 27, and then when I'm done with that, I raise it to the positive 2 power, or to the 2nd power. So what happens here? This is 1 over, the cube root of 27 is 3, and 3 squared is 9. So I'm left with 1 over 9x to the 4th. Okay guys, that is as much as I have here for this video. By the end of class, with this video, rewind it, go through it, pause it where you need to. You should be able to complete the packet. Turn this in please to your sub by the end of the period, and have a nice weekend.